In modern proteomics, the mass spectrometer is the key piece of instrumentation that allows the global analysis of complex proteomes to happen in a reasonable time frame. This presentation is all about how mass spectrometers actually work, because you need to understand how an instrument generates data before you can properly interpret the data. The first question is, why is mass so important for identifying proteins? Each element in the periodic table has a unique mass. In this table, listing the masses of the main elements making up organic compounds, such as proteins, it can be seen that each element and the isotopes of those elements have a unique mass. The difference can be averaged to 1 Dalton, or the mass of a proton or neutron. Carbon has 3 isotopes, which vary by the number of neutrons in their nuclei, but otherwise they are chemically identical. The carbon-13 isotope is only a very small proportion of the total carbon on the planet, but it is extremely important for mass spectrometry, as we will see. Because elements have unique masses, compounds made of those elements can also have unique masses. For ethanol, when the masses of the elements making up ethanol are summed, the compound's molecular mass can be calculated. This can be repeated for carbohydrates or other organic molecules such as this toxin from potatoes, and more importantly, proteins and peptides. The mass of a peptide can be calculated from its sequence by summing together the masses of each amino acid. But what if we don't know the sequence of the peptide? This is where the mass spectrometer becomes useful. Mass spectrometers measure the mass of ions, which are charged particles. So unless you can either add a hydrogen atom to an amine or remove a hydrogen from the carboxyl group of a peptide, you cannot measure its mass. Mass spectrometers consist of 3 basic parts that can be put together in different combinations to make specific types of mass spectrometers that are useful for specific types of analyses. First, you need something to generate the ions, called the ion source. Then you need something to measure the mass of the ions, sometimes called a mass filter. Combinations of mass filters can be put together for different purposes. Lastly, you need something to detect and count the ions. The mass filter and detector are always under vacuum, so that random molecules floating around in the air don't get measured. Once all of this happens, a spectrum is generated, in this case for solanin. The spectrum shows a number of populations of molecules, with each peak being the accumulated signal of hundreds to thousands of molecules of exactly the same thing. The major peaks show the molecules of solanin, whose carbon atoms are all the C12 isotope. The next peak, appearing at 1 Dalton larger, are the molecules of solanin that have 1 carbon atom with an extra neutron, the C13 isotope. In different molecules, the C13 atom can be at a different place in the structure, but the mass of the intact compound will be the same. Thus, we can see the accuracy of the mass spectrometer that can measure the difference in mass to less than the mass of a hydrogen atom. The difference in mass between the C12 and C13 isotopes of ions is important when measuring peptides. Mass spectrometers don't measure mass, but mass divided by charge ratios, or M/Z. So for solanin, which takes up a single proton to become an ion, the mass over charge ratio for the C12 ion is 868.5 divided by 1 charge, and the C13 isotope with its extra neutron is 869.5 divided by the 1 charge. Thus the difference in mass between these isotopes is 1 Dalton, reflecting the mass of the neutron. Peptides, such as this one, because they have 2 primary amines, can take up 2 hydrogen atoms and thus have 2 charges. The calculated mass of this peptide sequence is 1570 Daltons, but the mass spectrometer measures the mass divided by charge ratio for the C12 isotope of 785.8. This is because it is measuring the mass of the peptide plus 2 hydrogen atoms divided by the 2 charges of those hydrogen atoms. The C13 isotope containing the extra neutron of the peptide is measured as 786.3, or half a Dalton larger than rather than 1 Dalton, because the mass spectrometer is measuring the mass of the peptide plus a neutron plus 2 hydrogen atoms, and then dividing it by 2 charges. The mass spectrometer can now be programmed to use this as a selection device, looking for half Dalton or less differences between adjacent mass peaks to select ions for further analysis. Now that we've got that sorted out, it's time to look at the ways of getting peptides into the mass spectrometer, or looking at the ion sources. The first we will look at is matrix-assisted laser desorption ionization, or MALDI, invented in the mid-1980s by Franz Hillenkamp and Michael Karras. In this technique, the peptides are spotted onto a metal target plate with an ultraviolet light absorbing compound called a matrix, and allowed to dry. The two main matrices used are alpha-cyanosinaminic acid, or CHCA, and synapinic acid. The plate is then put into the mass spectrometer and a high voltage is applied to the plate, about 15 kilovolts. A UV laser is then fired at the sample and energy is absorbed by the matrix, which transfers this energy to the peptide molecule. This ionizes the peptide molecules off the target plate and they are accelerated past a counter electrode at 12 kilovolts into the mass filter, which is normally a time of flight detector. It is important to note that MALDI predominantly generates singly charged ions, not multiply charged. Time of flight is the simplest form of mass filter, measuring the time it takes for an ion to travel from one end of a tube to the other end and strike a detector. The laser pulse starts the clock, and an ion striking the detector is the measure of time. The larger the ion, the slower it travels. The mass can then be calculated by inserting the flight time into this equation. Essentially, it's like measuring how long it takes for something to get from slingshot to target. As with everything else we've discussed, we are not measuring a single ion of a particular mass, but hundreds to thousands of molecules of the same identical peptide. When the plume of ions is first produced, they are spread out a little in space, and thus time. At the detector, the number of ions hitting the detector is measured in bins of half a nanosecond. After a specified time range has been scanned, we can connect the intensities together to draw a peak, the apex of which is the mass of an ion. All of these intensity lines are the result of the same mass ion hitting the detector, but at slightly different times over a few nanoseconds. Thus, to increase the accuracy of the mass measurement and increase sensitivity, we want all of the ions to hit the detector at the exact same time, making the peak as narrow as possible. The first place to compress the ions into a smaller space is at the ion source, using a technique called delayed extraction, where electrical pulses are used to allow lagging ions to catch up before entering the time of flight tube. Another way of compressing ions is to use an electrical reflector. This uses an electrical mirror to reflect the ions back to a detector. This does two things. Firstly, it makes the flight path longer so that ions of slightly different masses are better separated in time. Secondly, it compresses the ions of the same mass together in space and thus time, resulting in a sharper peak for a mass. The difference between a linear TOF and a reflector TOF can be seen here. These are both the same set of peptides, the lower trace being linear TOF and the upper trace being the reflector TOF. The insets are a zoom on the same specific peak. In the linear TOF, none of the isotopic forms of the peptide can be resolved, whereas the reflector TOF is able to resolve the C12 isotope from the C13 isotope with ease. The alternate form of ion source is electrospray, again invented in the 1980s by John Fenn. In electrospray, the peptide or protein is in a liquid that flows out of a capillary that is under high voltage, usually between 1500 and 5000 volts, depending on the flow rate of the liquid, with a lower flow requiring lower voltages. For peptides and proteins, the liquid is normally an acidified mixture of water and organic solvents such as acetonitrile. The acidic conditions means that there is an excess of hydrogen ions in solution, and the peptide molecules become protonated on their primary amines as previously described. As the liquid is sprayed, it forms a plume of droplets that rapidly evaporate, making the droplets smaller and smaller and pushing the positively charged peptides together closer. The molecules of the same charge don't like being too close together, so there is a point where the charge density becomes too high, the Rayleigh limit, and the droplet explodes, leaving the ions to accelerate into the mass analyzer, often a quadrupole that can be placed before a time-of-flight detector. Electrospray generates multiply charged ions, as seen in this example of lysozyme, which has an intact mass of about 14,000 daltons. As mass spectrometers measure mass divided by charge ratios, the ion masses here show a population of lysozyme ions with either 7 charges, 8 charges, 9 charges, 10 charges, and so on and so forth. To determine the mass of the lysozyme ion with 1 charge, and thus its true mass, we can use simultaneous equations. Computer algorithms exist to perform this task much faster. Thus, electrospray can be used to very accurately measure the mass of a protein using a mass analyzer with a relatively small mass range, which makes the mass spectrometer more sensitive. To illustrate the main difference between MALDI and electrospray, we can observe these two spectra of myoglobin, a protein with a mass of 16,952 daltons. In the upper spectra from MALDI, we see the singly charged ion at 16,952, and an ion of myoglobin with 2 charges at half of that mass. In the electrospray spectra, we can see the multiple charge states of different populations of myoglobin ions. The main advantage of using electrospray is that it can be interfaced with liquid chromatography more easily than MALDI, but we'll discuss this further when we have discussed chromatography in more detail. Electrospray is most often interfaced with quadrupole mass filters, although ion traps were very popular for a long time. We will discuss those briefly later. A quadrupole consists of 4 rods arranged in a square that can have different amounts of voltage or radio frequency applied to them. At a certain voltage and radio frequency, a certain mass-to-charge ratio ion will be passed through the quadrupole to a detector, while other ions are lost to the vacuum system. To scan a mass range, the voltage and radio frequency must be varied, and so sensitivity is reduced. So why would you use a quadrupole? Quadrupoles are fantastic at selecting specific mass-to-charge ratio ions and transmitting them to other types of mass analyzers. One configuration is the triple quadrupole shown in this diagram. The first quadrupole is used for ion selection, for selection of a specific ion, with all others being excluded from the quadrupole. The selected ion is then transmitted to the second quadrupole, which is a collision cell. This cell is filled with nitrogen gas molecules, and the ions are accelerated into the collision cell, where they collide with the nitrogen molecules and get smashed into fragments. The fragments then get transmitted to the third quadrupole, which is set to transmit only 1 fragment to the detector, while the rest are lost. The result of this is an extremely sensitive and specific assay called selected reaction monitoring, which can be thought of as doing a Western blot with a mass spectrometer. It requires that you know the identity of the peptides that you want to measure to program the mass spectrometer. In other words, you can target specific peptides in a complex mixture. These spectra represent full scans of the intact peptides selected by quadrupole 1 and the fragment peptides selected by quadrupole 3. However, the output is a time-based chromatogram showing when the ion selected by Q3 is detected, and this can only happen when the intact peptide is present and selected by Q1 is transmitted to the collision cell for fragmentation, and a specific fragment is transmitted by Q3 to the detector. These combinations of Q1 mass and Q3 mass are referred to as a transition, and the mass spectrometer can be set to scan transition combinations for about 50 milliseconds before moving on to a different combination for another 50 milliseconds. Thus, a list of a few hundred transitions, and thus peptides, can be scanned through over a few seconds, allowing numerous proteins to be assayed in the one experiment rather than one at a time for a Western blot. But in the majority of proteomics experiments, we do not know the identity of the peptides or proteins, so we need to operate the mass spectrometer in a discovery mode using scans of a mass range. As mentioned, quadrupoles do this poorly with low sensitivity and resolution, so hybrid instruments are often used. One of the most popular is the quadrupole time of flight hybrid, which is shown in this diagram. It consists of the front two quadrupoles of a triple quadrupole instrument, the Q1 for ion selection, and the collision cell for measuring for fragmenting peptides. The third quadrupole is replaced with a time of flight mass analyzer. As mentioned earlier, the time of flight requires a start time to measure the ion's flight time, but using chromatography to produce ions at the source means that ions are continuously flowing through the quadrupoles. We create a start time by making the ions turn 90 degrees into the TOF. Every 250 milliseconds, the pusher pulses a packet of ions into the TOF. The ions fly down to a reflector and are reflected back to the detector. Thus we can scan a mass range and get high resolution data. This animation shows things in more detail. All of these balls represent ions. The grey ones represent uncharged ions that will get sucked out by the vacuum system. The positively charged ions will continue from the sampling capillary through a series of electrical lenses into the quadrupoles. In the quadrupole here, the only ion being selected is the green one. All of the rest are being excluded by the vacuum system. The green ion has been selected and then transmitted to the collision cell, where it will collide with nitrogen gas molecules to produce fragments. You can see the nitrogen gas as the hazy things here, and you can see the fragmentation of these green ions occurring. The fragments then get transmitted out the other end of the collision cell to the time of flight tube. The fragment ions are compressed into a nice flat packet before they reach the TOF tube, so that all of the ions have the same starting time before they are pulsed into the TOF. As you can see them rising straight up, they all have the same start time, and ions of the same mass stay together, but ions of different mass have a different flight time. They get reflected back from the reflectron and down to the detector. They strike the detector and cause a cascade of ions, which is then measured by a photomultiplier tube. Thus, different mass ions are detected in bins. There are not many uses of cyclotrons nowadays, because the problem with them is that they're very expensive to run, as the magnets require cooling with liquid helium. In proteomics applications, they have been replaced with an alternative type of cyclotron called an orbitrap, which does not have a magnet. In an orbitrap, the ions circle or orbit around a central spindle, again inducing current in collection plates, which is then interpreted by Fourier transform to produce a mass spectrum. More detail on how these works can be found in this video from Thermo. As with quadrupole TOFs, orbitraps are most often used with other mass analyzers as a hybrid. The original instruments produced were paired with ion traps, which we are not going to discuss any further, except to say that they are able to trap specific ions and fragment them in the same space, unlike a quadrupole which transmits ions to another quadrupole for fragmentation. Recent orbitrap-based instruments use the orbitrap for scanning a mass range to measure intact peptide mass before using a quadrupole to select a specific ion and fragmenting that ion in a separate collision cell before transmitting the fragment ions back to the orbitrap for measurement. For proteomics purposes, either a quadrupole TOF-based or an orbitrap-based mass spectrometer would give good data, but specific differences can make one type more useful for certain types of analyses. While the orbitrap incorporates a detector by inducing a current in detector plates, triple quads, quad TOFs and ion traps need detectors after the mass analyzer. Triple quads and ion traps use dynodes where a charged ion hits an electrode, creating a secondary electron that increases or amplifies the signal. The mass is determined by the software knowing what the voltage and the radio frequency of the quadrupole was, and those values determine a certain mass. Time-of-flight analyzers are coupled with microchannel plates. A charged ion hits the front of the plate and causes a cascade of electrons to hit an electrode, resulting in signal amplification. The mass is determined by measuring the time from the start signal, coinciding with the ions being pulsed by the pusher, and the ions of a single mass hitting the detector. We revisit this diagram from earlier, where ions arriving are counted in bins of half a nanosecond. After enough time has passed to measure the desired mass range, typically 350 to 1500 Daltons, the intensity bars are joined to produce a spectra. This concludes our very basic introduction of how mass spectrometers are used in proteomics work. In the next presentation, we will discuss how the instruments can be used to solve questions in proteomics.